Oh yes, so we were okay. I won't go there then. I did a formal Lab 5, the conditions for a final project, and as usual there's going to be a breakdown that depends upon work habits. 30% depends on project demonstration, grade, and 50% is based on the project write-up. And there is the caveat that if we observe differential work in a group, we may grade differentially within a group. There will be a formal write-up which will be in the form of a web page which you are required to submit. For MEng, I can require submission. It's your intellectual property, but you have to give me the report. You can, however, if you have intellectual property in the form of code or schematics, you can withhold those. Tried to come up with some ideas that would be interesting. We've talked about the idea of a pulse oximeter and ECG to get vital signs. That would be interesting to do. A Doppler. I'm not sure all these are possible in our lab conditions. A Doppler blood flow meter. You blast ultrasound into a vein, and you watch the Doppler shift coming back, and that gives you the velocity of the liquid. Blood pressure cuff. That would be interesting to do. That has some mechanical aspects. Another possibility we've been talking about here is using capacitive electrodes on arm or fingers. That would be interesting to do. I think the hard part is noise, but I'm also willing to put some money into fabricating electrodes. The idea of being able to record off of 2 fingers with no electrical contact, touching nothing but circuit board, is attractive because it's sort of inherently safe. And if it could be done in a reasonable fashion, that is to say not too high in noise, that'd be a very cool thing to do at all levels. There's this interesting idea of using passive RF coupled sensors for ECG. I would like to see if that can be done. Again, I'm not entirely sure how to do that, but there's lots of papers out there on it. As more of a software project, take an ECG and do an advanced QRS detection, which is to say Pan-Tompkins is your starting point. And then look at schemes for QRS detection which are newer, better, presumably by validating the detection against the MIT database and then getting live data off of it from yourself. And in all of these, I'd like to see real hardware being built, not just an abstract simulation of a hypothetical process. Electronic stethoscope and heart sound analysis would be interesting to do. I've had people build electronic stethoscope by cutting apart an acoustic stethoscope and ramming a microphone up the plastic tube. Works nicely. But the heart sound analysis is quite different than the ECG or plethysmograph, because what you're listening to is the noise from the valves closing mostly and the motion of the blood. So it's quite a different diagnostic that comes out of it. So something about turbulence. And if you want to be a little more abstract, build a transistorized hardware model of the heart where each cell now is represented by 3 to 5 transistors. Build enough heart cells that you can model a pacemaker and maybe even fibrillation, and then show how to defib it. I don't know how many cells that would take. I think it would be probably several, maybe dozens, in which case it wouldn't be possible. Could try and do a skin impedance measurement. Galvanic skin response is one old style. It's the basis of the original lie detector. If you're under stress, your skin impedance goes down because you sweat more. There's an advanced version of this called impedance tomography. If you were to put electrodes all the way around your chest and put current through pairs of these and measure the resistance between them, then you could get n different independent resistance measurements, and you should be able to back out some estimate of the distribution of resistances within that slice. Just like computed tomography with X-rays gives you a 3D view of the slice, or magnetic resonance imaging gives you a 3D view. Computed tomography, impedance tomography, can give you a 3D view into a slice, particularly where the slice has dramatically different impedances. What in your body would you guess has the biggest impedance discontinuity? Where, as you go through space, the impedance suddenly changes. Stomach's probably a good bet because the pH, there's a pH jump across the boundary and there's lots of ions inside. But what about lungs? There you have almost perfect insulator inside the structure, and impedance tomography is in fact often used on thorax by immersing the person in a tank and then putting electrodes around their chest, near their chest. So I don't think you could do dozens or hundreds of electrodes. People also do ultrasound tomography, where you put ultrasound sensors all the way around the body and then pulse from different locations and get an ultrasound image. Ultrasound and impedance tomography are interesting because they do, particularly ultrasound, notices interfaces, whereas X-rays get volume information. X-rays are proportional to the density of material. Ultrasound is proportional to discontinuities in the density, first derivative of the density, so it gives different information. You might be able to do 2 or 3 electrodes. Let's say you put electrodes around your arm. You might be able to get an impedance distribution inside some small structure. For instance, in an upper arm, could you find the bone? Looking at eyes, it would be fun to try and make an eye motion measurement by infrared or camera, or electroocular effects. Your eyeballs are dipoles. As you move your eyes back and forth, the voltage across your face changes. Could you set up a measurement scheme for that? Oh. Where do you hook them up? Typically here, 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 and here. Maybe just one eye if your eyes are tracking. Snarcturization, huh? Characterization. Pupil servo. You have a servo, a light intensity servo. It would be interesting to do to understand the feedback characteristics of that servo. There's a paper from the 70s or maybe the 60s that that goes into that, and I linked that one up because it's a little obscure. And of course, since it is decades, 1956, almost 60 years old. Yeah, you could bet this was scanned. So there's the canonical control system with feedback, and then they talk about how to break the feedback loop using lights and photo transistors and so on to estimate pupil area. And then in the end they get the Bode plot of the pupil, the open loop response of the pupil. That'd be interesting to do. I probably wouldn't let you shine a laser in your eye. Oh, ECG with improved noise removal. What do I mean by that? Well, you have been redirected because... Oh, great. Okay. Oh, well, I am logged in as Cornell University, so I should be able to get to it. But I guess I better fix that link. So you can imagine also another possibility is functional imaging, and I'm not going to let you do CT scans in the lab because I'm not going to let you have X-ray sources in the lab. It's such a phenomenally bad idea. I got to tell you though, in junior lab in college, we had a high-power X-ray generator in the physics lab, and it was set up in a faculty member's office. And you'd run in, set up the machine, start it, and then run back out of the office again, so that you had the concrete wall as shielding, hold the Geiger counter in the doorway, and you could watch it go. People walking by just got it, you know.
So the knobs weren't shielded in a shielded area?
No, it was just an unshielded X-ray machine, and the shielding was the room we put it in, which was concrete block. Can you imagine trying to do that now? Oh my! Oh. The paperwork. Oh, no X-rays. Infrared tomography, functional near-infrared brain imaging, is a hot field right now. You can shine infrared light into your head, and you can get a reflectance back out, which is related to brain activity. Two people in the class did this as a 4760 project. They're not here today, or I'd tell them they can't do that. Or they have to use their hardware differently than they did in 4760 at least. Infrared reflectance has been shown to be correlated with muscle activity. It would be interesting to figure out how it's related to EMG. Now switching gears a little bit. There's various interesting aspects of oscillators. Oscillators are every place in biology. You have an oscillator which runs your walking periodicity. You have an oscillator which sets your hunger during the day. You have an oscillator which varies your insulin output during the period. You've got all kinds of oscillators at all time scales from milliseconds to years. And it would be fun to play with them a little bit. One possibility, if you want to go for pure hardware, is to make a model of a gene oscillator and figure out some dynamics of the gene oscillator, figure out how to model it in hardware, and then model it and see what its characteristics are. Another possibility is to look at nonlinear oscillator synchronization. And I didn't link up, there's Firefly videos available in which you can see whole trees blinking. But here's an interesting thing on synchronization in light-controlled oscillators using all analog. There's no computer here. It's all little analog modules that are built, and it's kind of a mess, but I think it could be made much more simply. And you put these things on the table and they all start blinking randomly, and a little while later they all phase lock and blink at the same time. And there is no central control. So building those and then characterizing it could be a good project. And then I guess we call infrastructure instrumentation projects. Is it possible to build a completely analog adaptive 60 Hertz filter? And I'll talk about adaptive filters a little bit today. There are all kinds of adaptive filters for ECG, EMG, digital filters. Implementing and playing with them and figuring out which ones work the best would be an interesting project. One thing I'd be interested in is eliminating the DAC 6008 interface so that we could just use the audio input to the computer. Audio input's a 16-bit ADC and DAC. It should be able to do everything that the DAC 6008 does, except the default audio interface on the computer only goes down to about 50 Hertz. So you can't get anything interesting about heart or anything else because the frequencies are too low. So what do? You build an interface that goes on the audio channel, which is a voltage controlled oscillator that produces a tone proportional to the input voltage very accurately, so that DC signals now become 1000 Hertz, and minus 10 millivolts from that becomes 950 Hertz, and so on. Then you feed that into the computer, where an algorithm, presumably in MATLAB, would then decode the frequency back into a voltage. So now you're looking at essentially a modulated signal, decoding a modulated signal. So that it would be possible to build a rather small, cheap interface that anybody could use for doing bioinstrumentation without spending $170 for the DAC 6008. And there's various possible joint sports kind of projects. Wireless knee angle sensor, all analog, no microcontrollers. Then some acoustic projects. Again, I'm not sure that these are possible. I think they're possible. There's otoacoustic response. Your ear produces noise. Do you all know how the ear works? You remember that from physiology? There's a membrane in your inner ear which is tuned over a large dynamic range of frequencies, and relative motion on this membrane, called the basilar membrane, shears hair cells, which, when sheared, produce a small output voltage. And you can show that the system can't possibly work unless there's gain in that system. The tuning is too sharp for a passive filter. There is gain. And in fact, on the basilar membrane are little cells that act as motors to drive the basilar membrane. under certain circumstances, you can hear the output of those motors. They're in acoustic, they're in audio region coming out of your ear. Takes a sensitive microphone. I have no idea what the levels are, but it's kind of an interesting effect. I don't know how you do the measurement. Pardon me? Well, you stick a mic in your ear as start, right? But I don't know what else you have to do. Any of you have tinnitus, where your ear suddenly makes a tone? Acoustic. Suddenly you'll hear boop for a few seconds, or hopefully only a few seconds. Some people have that tone never goes away. Drives people nuts. Do any of you have that effect? You hear it sometimes, occasionally? Lasts for a few seconds.
I don't know if I actually call it tinnitus.
Where you'll suddenly get a tone coming. You'll suddenly hear a tone, and
To me, it's more of an absence of noise.
so you suddenly things get quiet.
No, so like if I'm in a room with no noise from them, right? I can hear something ringing.
Interesting. Have you ever tried to have somebody else listen to your ear and see if they can hear it?
No.
Because some people make enough noise that you walk by them and you can hear sound blasting out of their ear. It's fairly rare. I mean, it happens with people with hearing aids all the time. But I'm saying with people without hearing aids.
Would that mean their gain is higher?
Yeah, their gain is high enough that they're oscillating. They're doing limit oscillation, so it's high power output. Usually these people are close to deaf, so they don't hear it. So I have that every once in a while. The symptom is that I'll get a loud tone in one ear and the ambient noise is suppressed at the same time, and then the tone fades out and then my gain comes back up and I can hear again. And I told my wife when I first met her that if I ever grabbed her head and pushed it against my ear, don't say, "What the hell are you doing?" Just listen carefully. And she's pretty compliant. And you have to wait a long time for this to happen. We were in a movie or something. I can't remember. It was so quiet. I had an arm around her like this, and I suddenly got a loud tone. I went, wham! Pushed her against it. And she goes, "Nope." And we go watch. So she completely complied on no notice. I was very impressed. I expected kind of to get punched or something, but but it'd be fun to try and measure this effect for real. Measure the head-related transfer function. So you each have a bandpass characteristic that's caused by your head and face and shoulders and so on, that allows you to tell where sounds are coming from. You can measure that by putting a microphone in the ear and then applying an impulse function to the system from different angles. So you put a loud click out of a speaker from different positions in space, and then you ask, what is the frequency response of the resulting system, which includes your head, ears, hair, and the microphone. Try and deduce the head-related transfer function, and then use that to take a sound and make it sound like it's coming from someplace in space.
I know people have taken like a mannequin of a head with the folds of the ear, put microphones in the ears, and you can shake like a matchbox around.
Right.
And it's completely stereo, but you get this 3D imaging. It's really cool.
Yeah, and you can, and that's been done with actual humans too, at a couple of locations. You take little microphones and you crazy glue them into the person's ear, and then you play impulse sounds, and there's a database of something like 50 different heads that's available, as well as mannequin heads. But it turns out that if you use convolution to calculate the filter effects on a synthesized sound, the best effects you get is when the measurements are taken off your own head. So I think that there's if you figure out how to do this cheaply, then you have a startup. right? You do this, you somehow have a utility which uses your smartphone to get the head relay transfer function. You send it to some location that processes it and then puts it into your MP3 player to spatialize your MP3 player. But just measuring this would be interesting. I don't know if it's, I don't know how accurately you could do it in the lab. You know, there's lots of problems with it, including small microphones. And I guess I wouldn't allow you to crazy glue microphones into your ears. But you could put them probably near your ear. I think that would be acceptable. So any of these sound like fun? What are you thinking now for final projects?
So, is there anything where using the EEG data, like if you think right, suppose you think that the right LED should blink, then it actually blinks using the EEG data. So can we do something about that?
EEG is generally hard. I won't let you put, I'm not inclined to let people put lots of electrodes on their head. The noise level, the signal level is now microvolts instead of millivolts. So everything has to be 1,000 times quieter. It's fairly hard to get anything. I have seen it done. I've seen people get alpha rhythm and control a game with it. But you're certainly not going to get enough information out to put to do any sort of map. It's going to be 1 channel or 2 channels only. Any other thoughts on this?
Have we done the electron stethoscope and heart analysis project?
Uh-huh. So you...
I've never done that. I was considering it.
I've seen the
electronic stethoscope.
Electronic stethoscope. I've seen people do it in 4760 a couple of times. The first time was a decade ago, and it was sensitive enough that you could get the pulse off of the carotid artery, which is extremely loud, but not off of the heart. The second one was done last year or the year before, and was sensitive enough to get heart sounds directly from the chest.
How exactly did you measure that? Did they just use an actual stethoscope?
They bought a stethoscope head, cut the tube that went to the stethoscope. So you have a stethoscope is a mechanical amplifier. It has a membrane here which has a large diameter. You go off to a small tube and you have a fairly small amplitude here that turns into a large amplitude here because of the ratio of the diameters. The ratio of the diameters is probably 10 to 1, so the gain is 100 to 1. It's 20 dBs or 40 dBs depending how you count it. Usually a rubber tube that goes off to a pair of ear plugs here, and what the students did was to cut this tube and ram a cartridge mic into the rubber tube about 1 centimeter, 2 centimeters from the head, and it worked quite well.
You get good signal from there as well.
I don't know that they tried it. They could get the heart sounds directly from the chest, and it was pretty convincing. Get a lot of information about valve motion from the chest. You can also do this. You can hear quite a lot of heart sounds if you slap your ear directly against somebody's chest. You get a fair amount of gain that way. It's just not very handy, and you can actually get a little more gain from an electronic system. You can hear a little bit more. And of course, then once it's electronic, you can use selective filtering to get rid of noise and to emphasize certain features. Yeah, it's a good project. What you want on here is a very quiet audio amplifier. So you want to find an op amp or an audio amplifier that's low noise. And so you can turn up the gain quite a lot and hear what's going on. And it would be interesting to do two of these and put one on the chest and another one someplace else and look at the P wave, you know, the sound propagation velocity, various other things. Any other thoughts about this, about projects?
Yes, with making the night interface, is there a way to like select different something?
So the sampling rates, if you're sampling through the audio port, you can sample at several standard rates that are more or less determined by Windows. The standard rates are 8,000 samples, 16,000 I think, 20,000, 44,100, and there may be one more in there. MATLAB also allows you to subsample that, so you can sample more slowly in MATLAB if you want. So yes, you can choose the sample rate in software. And what you have to do then in hardware is to upconvert very slow waveforms into FM. So you're going to FM modulate a waveform. And for the faster moving stuff, you want to transduce that directly into the other channel. So you might put this into the left channel and this into the right channel. And there's going to be some set of filters that looks like this on the input, so that the slow channel is low pass filtered and the fast channel is high pass filtered, with about the same, with a crossover point where you're not going to lose any data. It's coming in one place or the other. But there's got to be some sort of safe crossover area.
I have an external music DAC in it. I know if you can run that backwards and take advantage of the 24-bit 9600 sample rate.
96 kilobaud.
Yeah.
I have no idea. You probably can. There are certainly 24-bit digitizers built into some audio boards in computers, although I think most of them are 16 bits. The nice thing about using audio input is it's effectively free. Right. It also avoids the data acquisition toolbox in MATLAB, because sound input is supported directly from MATLAB without having to use the DAC toolbox, which cuts down cost and complexity a little bit. So what do you think?
Is there a way where we can put something in the shoe and understand when a person is running or something, like a gate analysis or something?
Gate analysis is interesting. So you'd want to, yeah, you can put accelerometers on the top of a shoe or in the heel. Actually, heel is a horribly hard environment. But on the top of the shoe is pretty good, as long as it's Velcroed tightly to the shoe, and you can get quite a lot of information about gait. At least you can get the foot acceleration in all axes. You can't necessarily get knee twist or hip displacement so much, although you could instrument several places. Given that the course is set up to be primarily not a microcontroller course, then you have to figure out how to telemeter the data off the human in analog form. There's a couple of ways to do that. One is you build a pulse width modulated transmitter and just send the data off analog as a pulse width modulated waveform. Another way is to use FM modulation. You send the low frequency wave as a modulation on an FM signal. You can build an FM transmitter for about 10 cents by using a Max 2606 part, which is it's effectively an FM transmitter in an SOT23 package, so it's 3 millimeters by 3 millimeters. It's just big enough to solder. You put a voltage into this, and the voltage sets the frequency. You can tune it to 100 megahertz. You can have the voltage vary the frequency back and forth. You have a wireless interface to a voltage. In fact, maybe you could use that for ECG. As long as you stay low power and you don't put an antenna on this, then you're not violating FCC regulations. If you slap an antenna on one of these guys, nice high gain antenna, and start broadcasting music, somebody's going to come knocking at your door, because that's illegal. You can get out several hundred feet with this thing, maybe half a mile. But it's a very nice little transmitter. Oh, and Maxim-IC, Maxim Semiconductors, will sample you 3 of those by overnight mail. I've had several students build transmitters using those. And then the receiving end is just any FM radio you happen to have laying around. Then the FM radio gets connected to the computer or decoded. The audio gets decoded off of it, but the wireless link is extremely cheap. One-dimensional, one-directional, analog.
How much range does this give?
More than you can legally use. At least hundreds of feet with a folded dipole. Much more than that with a beam, with a Yagi, with a beam antenna.
So is there a branch that's like actively checking what the frequency and seeing if people are illegal broadcasting?
Is there some guy in a truck driving around? Typically not, but what gets you are complaints. Because you happen to be your signal, which is strong and therefore you hear it, happens to also interfere with WVBR. And some guy in the dorm says, I don't know what's going on, but I can't get WVBR because this jerk is broadcasting warbling tones all the time. And then somebody's liable to bring a sniffer around and go looking for you. And if you're doing pirate music, then that's much more likely to happen. If you're identifying yourself. This is Akshay broadcasting from Phillips Hall with your greatest hits from the 50s. You know, you're asking for it. Here's my office number, give me a call for requests. Then
It's not American music. Looks like Bollywood songs.
I don't know. I don't know what the copyright situation and copyright agreements with India are, but it's you know, stations like that are liable to get shut down, and I think it's $10,000 a day fine for operating an illegal transmitter in the U.S. So you need to, if you're going to operate a transmitter, in fact, one of the pieces of the final project report will be, if you're operating a transmitter, you have to be able to prove to me that you are within FCC regulations. So you need to read Part 15, FCC Code Part 15, low power transmission. It is an evil piece of writing to understand. But I'll help you with it. Cell phones are transmitters and receivers, sure. They're quite actually quite amazing transceivers.
I wonder if you could create like use the digital scope, have that use the MAX 2606 and have the data be sent to your iPhone or Droid and have it analyze everything for you.
So there's a question of how would you get data into your phone? You could put it in through a audio channel. Is there a microphone input? Yes. You could put this in through a microphone channel and then do the demodulation, do the detection in an Android app. You could, and then all you need is a audio connector going into the phone and then an app that can listen to the audio. I think Android 3 and above has a published SDK for getting to the USB port, and that's sort of outside the region of this class, but you can hook relatively arbitrary I/O connections to it. In fact, I think there's a device called IO-IO, isn't there? IO-IO? Google that up. I think there's a little box that's meant to go onto an Android phone that gives you analog and digital input for a few dollars, a few tens of dollars. I think next time I teach this, I am going to require 4760 as a prerequisite and open up the labs to microcontroller work as well as big computer work, as well as MATLAB work, because so many of these things are obvious microcontroller or cell phone applications. Maybe we ought to just go to Android directly.
Is there a way where we can modify the current braille for the light? The device called braille.
Yeah. What do you want to do with it?
So can we just modify it and make it more better for electronic?
So I don't think you can modify the standard Braille as a standard. What you're asking is there a way of outputting it in any sort of electronic device? It's a touch interface, and there are ways of doing that. People are working currently at trying to make cell phones that have bumpy surfaces, have real-time bumps change on the surface by injecting fluid into fluid pixels, so they'll be called flixels or something. Fluid pixels under the screen that allow the screen to raise and lower. And you could imagine then that you could read Braille off the screen. I've also seen schemes where you raise pins up and then drop them again. Those are clunky usually, but a good electronic Braille interface would be interesting. But I don't think it's instrumentation oriented enough for this class. And I have no idea how to do it in any kind of cost-effective way. Anything else? Final projects? How's Lab 3 going? Everybody got loose connection. If the hardware is working and it stops working, it's almost always a loose connection. Almost always. A broken wire. These wires do break inside the insulation. Fairly rarely, since we upgraded our wire. Used to be fairly often when we were using cheap wire. You wouldn't think it, but you can buy cheap wire. It's very brittle. You bend it 2 or 3 times and it snaps. And some of the... Pardon me?
The worst debugging situation ever.
Oh, and I have seen students... I've seen students pull the wire out, cut it, and slide the ends back in to the insulation. This will be fun. Toss it back in the used wire, right? Why? Because you can. But yes, so the obsessive debugger will measure the voltage at both ends of a wire. If it isn't the same, the wire is broken. You have few enough wires in your design, you could do that with every single wire. If you had a... Obviously, you're not going to do it with every single wire because you'll be able to narrow the bug down to a certain region of the circuit by what works and what doesn't. Start at the input, work through until you find the place it fails, then look for loose wires there. So it's worth doing under certain circumstances. I've seen whiteboards fail also. You plug in a wire into the whiteboard and it doesn't make a connection. And in that case, what you have to say is, does the voltage on the wire equal the voltage on the pin of the integrated circuit, which is plugged into the same spot? That doesn't happen very often, but it does happen, particularly after somebody has melted the board. Yes?
That's just an aspect. So we had that same problem in a current region where the board was melted. I was wondering, how do you melt the board?
How do you melt a whiteboard? Well, you plug a transistor into it, a big FET transistor that can carry, say, 50 amps, and then you short it across a heavy power supply. And it'll go to the short circuit current of the power supply, maybe 50 or 100 watts. The whiteboards are rated at 1 or 2 watts. The connectors inside the whiteboard tend to be the highest resistance spot where they pinch the wire going into the hole. That tends to be a fairly high resistance. Most of the heat loss is there and it melts the plastic. I've seen them get hot enough that they smelled, that you could smell them burning. Typically we throw those away once they've burned. But every once in a while you'll find one that got thrown back into the drawer there. So everybody's getting data at this point. Good. All right. Well, let's talk about adaptive noise cancellation. You may need this for the ECG part. Has anybody tried yet to get an ECG off your arm instead of EMG? Again, I'm going to suggest that you take those electrodes, the circle of electrodes, cut one of the electrodes off of it, put one electrode right up in here, and the other two down here someplace, so that you have a fairly big distance between them. So ground and neutral will be down here, recording electrode will be up here, positive recording electron will be up here. And you should be able to get a bigger voltage difference for ECG than you would if you were just putting electrodes in a small band right around here. Clearly, you're going to want to relax your arm because any EMG, any place in your arm, is going to contaminate the signal. So you're going to want to relax your arm, lay it on the table, keep all the muscles relaxed. If you scratch your head, use your other hand. And turn up the gain so that you can see fairly small signals, and you are going to have to use the optimized band passes we talked about for Pan-Tompkins. So you're going to need probably analog filtering with some sort of reasonable band pass, and then you can probably see it on the scope. You might be able, it would be interesting to just take the EMG electrodes while you're set up for EMG. Once you get a good EMG signal, relax your arm, turn up the gain on the oscilloscope, see if you see a heartbeat. The filters are set about, what are your filters set to right now? 50 hertz, something like that? 1 hertz and 50 hertz, something of the sort? You'll see heart in there if the noise is low enough. Just turn up the gain on the scope and see what you see. So, adaptive noise cancellation is a scheme for tracking the noise, the properties of the noise. So, for instance, if you have some signal coming in which is now contaminated by 60 hertz noise, and in all of this we're going to assume that the noise model is additive, that you're going to add the noise to the signal, and there's not going to be any nonlinear effects. There's no multiplication. You're just adding the signal to the noise. Then what you're going to get out is something that looks like this, which is the sum of these two, and you want to get rid of the noise as well as you can. But the noise may not be completely stationary. The frequency may vary a little bit, and the phase may vary a little bit. So that, well, one way of approaching this, I suppose, would be to do it by hand, where you have one knob. So you build a subtractor out here now. You build a subtractor whose other input takes the noise signal, modifies the phase a little bit, modifies the amplitude a little bit, and then subtracts it from the original signal. And I actually built one of these I didn't know about LMS at the time. I'm not even sure it was known at the time. But I built one of these in which I built a phase shifter for 60 hertz. How do you build a phase shifter? Phase shifter. So it could be an RC capacitor, right, which gives you a 0 to 90 degree phase shift. And then you have to adjust the gain to get rid of the attenuation, but that's okay. There's also a thing called an all-pass filter. An all-pass filter that has a frequency response, that looks like this, amplitude versus log F, but the phase shift looks like this. Where this might be 0 degrees. But in any case, some sort of phase shifter and then some sort of gain control. And with those two, you can by hand adjust two knobs, one for phase and one for amplitude. You do a two-dimensional optimization, and you can do that fairly fast with two parameters, and minimize the phase. And as long as the noise is stationary, that is to say it does not change with time, And as long as the phase shift and amplitude through whatever mess of mixing this is stays the same, then you've canceled the noise. I built one of these for 60 hertz and put it in somebody's lab over in biology. Yes?
Ultimately, how do you get the signal? Because I thought the problem is that when you get the input, the signal is combined with the noise. How do you separate the noise from the phase shift and amp?
Well, luckily,
Creating the signal that's 60 hertz
Well, so there's two approaches to this. For 60 hertz noise, you have a reference which is phenomenally close to what's contaminating your measurement by just putting a plug in the socket. So you take power directly off the 110 line, step the voltage down to something reasonable so you don't kill yourself, transformer isolate it, and take that sine wave as the noise reference. So because we're using line, because a lot of our problem is going to be line related, we have a reference which is very handy, and we have pure noise. The other way to do it is you try and make an estimate of the noise from the mixed signal. I think that's called blind separation, where you try and guess what the noise and what the signal is. That's much harder. Everything I'm going to talk about assumes that you have a noise reference that you can subtract. Yes?
When you say the noise is stationary, do you mean like the distribution of the noise is stationary?
It is not time varying. I mean, it's stationary in a statistical sense that if you look at one piece, it's pretty much statistically like the next piece.
It's not exactly the same in time, but it's
Statistically the same in time, yeah.
Have you had a positive phase shift?
Differentiator. So a low pass filter always has a negative phase shift. A high pass filter always has a positive phase shift. So an all pass is going to be some combination of those where you adjust the time constant so the amplitude doesn't vary. So clearly what we would like to do here is we would like to make the adjustment of the phase and the amplitude automatic, so that I don't have to sit there and say, the noise came back, I'm going to vary the knobs a little. I once built a system where I wanted extremely low noise with a real fast system. And I got the noise down to about 10 microvolts total into the input of the amplifier by putting window screen in the lights, and by taking my computer monitor apart, this was still a CRT monitor, and putting wire screen inside the box and over the front of it so you could see the image but poorly. You flip it up and look at it and then flip it back down again when you were going to record. Grounding every piece of metal in the room, including the bookcases. And the final way of adjusting it was across the front of my rack, the equipment rack that held all the hardware, was a big aluminum bar. This was made out of 1/2-inch aluminum stock. It was about 1 inch wide, and I put that on there to bolt other stuff too. And I clip a ground lead to here. And if I slid this ground lead along that bar, which had maybe a few micro-ohms of resistance from one side to the other, I could find a null point where the noise went away. And this ground went over to my table where the electrode was. And I could slide it along there and the noise would go away, and I'd record for a while, and then the noise would come back, and I'd slide it over here and the noise would go away, and then it would come back and I'd slide this back. And so the nulling was done by hand by sliding a clip lead along an aluminum bar. And that's how I kept the noise minimum. Someplace in the circuit, a subtraction was being done by something that canceled out the noise. I have no idea where it was. I mean, I built everything in the rack, but still, it was complicated enough. I didn't know where the subtraction was occurring, but it was occurring. That's no way to make money and to run a hospital. So you want to make the phase and amplitude measurements and compensations automatic. The question is, how do you do that? So I'm just going to give you one version, which is called an LMS filter. That stands for least mean square. Least mean square filter. And the model for it is that we're going to have some signal coming in, which is then additively corrupted by the noise, which we're going to call S and N. So this happens because of physics or because of geometry, not because we want it to happen. And then we're going to have some S plus N here, which is what we're going to record and we want to filter. Then inside of our box, what we're going to do is we're going to subtract off. We're going to subtract off the output of some adaptive system. So there's going to be some output here which we're going to call Y. And the adaptive system is also going to get the noise input. And it is going to be trained by looking at the output, which is commonly called the error in the system, but is in fact, we are going to, this is going to be subtracted and this is going to be added. The error is going to be the denoised signal. It's going to be what's left over after the adaptive system subtracts off whatever it subtracts off. So this error output then is going to be signal plus noise minus Y. And we're going to assume that all these signals are statistically stationary with zero mean. If we assume that the noise is independent of the signal, then the expected value of the square of the output, the expected value of the square of the output, mean square, is equal to the expected value of the signal squared plus the expected value of n minus y squared, n minus y quantity squared. And this is true because these are independent. If we assume that the signal is fixed, if it's stationary, and we minimize the error by changing y, if we minimize the error by changing y, then this error will be minimized when this is minimized. Clearly, if this is a constant. If we minimize this, we will have minimized the size of the output. So that minimizing the mean square of the output is equivalent to matching y to the noise. And if we manage to make y equal to the noise, then the E output, the error output, is exactly equal to the signal. And hence the name least mean squares. We're just going to try and minimize the value of the mean square error. And we'll have a solution. And the way this is normally done is to make a FIR filter, finite impulse response filter. We've talked a little bit about FIR filters, I think, in here. It starts to run together because I can't remember which class I've said which in, but we did talk about FIR filters, right? These are filters that are whose output is a function only of the inputs and not of past values of the output. So we're going to build an FIR filter with variable weights. And how do we get the weights? Well, first of all, let's write down that y at time I, then is going to be let me write out the general FIR filter again in MATLAB format as y of n is equal to b1 times x of n plus b2 times x of n minus 1 plus b3 times x of n minus 2, and so on, right? The output is now a weighted sum of the inputs. General FIR filter. So we're going to write this then as the sum from j equals 0 to n minus 1 as some weight j times n of I minus j, which is the same thing but compressed into a slightly smaller form. You can show that you can write the gradient. For this filter, you could take all the derivatives, write the gradient of the error, the slope of the error in multi dimensions, and find that if you were to change these weights at every time step in an appropriate way, that you will minimize the error output. And the appropriate way to change them is by saying that the weight at step I plus 1, and this will be the jth weight at time I plus 1. The jth weight is going to be the weight at time I, j. So it's going to be the jth weight at time I plus some small constant mu, called a convergence factor, times the error at time I, times n of I minus j. So, to turn this into words, we're going to keep a list of inputs of the noise corresponding to the inputs to the filter here. We're going to keep a list of inputs to the noise for at least j from some fairly long history. We're going to multiply by the current input and set the jth weight to that value. This has the effect of minimizing the correlation between the signal and the out. Let me make sure I'm saying that right. We want to vary each weight to maximize the correlation of Y with the noise. We want to maximize the correlation between Y and the noise. And this searches the gradient, if mu is appropriate size, such that when we add up all the weights and the history of the noise, we get a perfect copy of the noise. And you'll notice the key thing here is that neither of these formulas, these iterative formulas, requires you to estimate the signal, which you don't know because it's been contaminated with noise. All right, so we don't have to know the signal plus noise. All we have to know is the noise and the output from the adaptive filter. Okay, to make this slightly less abstract then, let's do a very specific example where we're going to take rewrite this as 2 weights only. We're going to rewrite this for 2 weights. We're going to rewrite this for the 60 hertz input signal and the signal which is phase shifted by 90 degrees. If you have the in-phase signal and the phase shifted signal, then you can, by superposition, get any phase shift you want, right? Because you have now you're adding a sine and a cosine. You can make any phase shift you want by linear combination of those. So we're going to take, so our signal input now is going to be the same as before, and Y is going to be the 60 hertz noise, which we're going to then run through some weight, multiply by weight W1, weight 1, and then add together to make Y, which is subtracted for the output. So, and then we're going to take a phase shifted version. In other words, we're going to delay 90 degrees, multiply by weight 2, and add these two to form Y. So this now is a specific implementation where we're taking the noise and we're saying the general adaptive filter is going to have n possible weights, but we're going to limit ourselves to just 2 weights, one of which samples 60 hertz directly, and the other one is a delay of 90 degrees. Well, what does that mean? Let's say we're sampling at 1 kilohertz, 1,000 samples per second. What's the period of a 60 hertz sine wave? It's about 16.6 milliseconds, right? So a delay of 90 degrees is just about 4 samples at 1,000 hertz. Right? So a delay by 90 degrees is really a list of the last 4 samples. So we're using the output of this delay is, if this is noise of I coming in, then this point is noise of I minus 4. Okay? Yes? No? Blank stares? So then YI, the new noise estimate, is going to be weight 1 times Ni plus weight 2 times I times Ni minus 4. And weight 1 is going to be updated by weight 1 plus some mu, which you have to choose, times the output at time I, EI, times the noise at time I. And weight 2 is going to be weight 2 plus the same mu times the noise at time I times the noise at I minus 4. Corresponding to the 90-degree phase shift. And as long as mu is small enough but not too small, these weights will slowly converge to an optimal solution. They have to be small because you don't want this filter to exactly follow the... Oh, we're past quitting time here, aren't we? Yes. Okay, I'll finish quickly and then go back to this next time. We don't want this to follow the input exactly. Rather, we want the system to slowly converge to a stationary solution. Typical values of mu that are chosen are 2 to the minus 10. So it takes 1,000 samples to converge. 1 second. Not so bad. Students implemented this very algorithm on a microcontroller, and it worked. Cancel out 60 hertz. Now, let's say that the 60 hertz line has some third harmonic distortion so that the actual waveform on the 60 hertz line looks like this because somebody's running some ungodly big motor someplace. A 2-tap LMS is not going to filter out the third harmonic. It's only going to filter out the fundamental. But it'll take the 60 hertz out for the cost of 2 multiplies. Interesting. We'll talk more about this.